today is the third day of our IEEE boot camp of analog IC design and under FOSSEE, and we have our guest speaker Vipul from Navia Labs. And yeah, so yesterday we saw about magic layout, physical layout, and DRC check. Now we will be looking into the verification of our design. So yeah, so over to you, Vipul. So this is the final day. So hope you have the final
Yeah,
uh, enriching session. And yeah, please feel free to ask anything if you have any queries or something. Hope to see your design in the tiny tip.
okay. Thank you very much, Samantha. So yes, today is our last day. I think we till in last 2 days we have covered first two aspects of any analog circuit which goes to basically to be developed on an IC in semiconductor technology. These are front-end design, which consisted of schematic and simulation and test pen creation, which we saw in first day. And yesterday we saw how to convert that electrical design into physical layout using magic. So these two processes are called front end design and back end design. And another aspect of back end design is also maybe you can basically collaborate it with the layout or maybe taken as a separately. But in industry, I think sometimes there's separate teams which look into verification part of your design. So this is what we call design verification for analog circuits. DRC, we had some look at it yesterday, and then there are LVS and parasitic extraction. So these will be the steps which you will see today. Yeah, so I think this is the journey which I talked about. Once the verification is done, then your design, if everything is okay, like your specifications are meeting and your design rules checks are clear, then it is ready to be fabricated. When I say ready for fabrication, it's not like just doing a layout of your op-amp and it is ready for fabrication. Obviously, there are some other steps also, but they are more of procedural things like building an IO pad or IO ring around the circuit. These are standard things basically, which comes with any technology or it's available with the PDK. Only choice designer has to make like what kind of IO pads they require. And then there are some other steps which needs to be followed, like doing a metal fill on your design layout. But in our case, since we are like we are planning to do this tape out through tiny tape out, so in our case, these things need not be taken care of. The goal or objective for people who want to send their design for fabrication is just to complete the layout of their block, whatever they are intending to do, and then they can submit us, and we will take over further from there for making it compatible for fabrication. Okay. But okay, just to give an idea, in industry we do have some other steps. Building an IO ring layout, seal ring is also put around a die layout, and then also metal fill needs to be done, and then there are some antenna checks needs to be done. So these are some of the other processes which are required before you can say like I have finally taped out my chip on my own. Okay. So this was a bit about DRC. So let me just quickly go through these slides. So just to give you an idea, like what we will be seeing today. So DRC errors, this is how we see in Magic that the count of DRC error, if they are appearing, they automatically pop up on the top. I think that's what I was mentioning yesterday. It's a good feature of DRC for Magic to give us on the fly DRC errors. And how the DRC errors are visible are like this. They are highlighted inside the Magic sheet. And if you want to understand or basically what that DRC error basically means, then these are the commands which needs to be typed in your console box, DRC find or DRC by, and it will give you an idea like what exactly which layers these DRC errors are pointing to and what is that particular error. So this is how you find it, and we will see these today also in our demo. Then this is how if you want to check if there is some error with respect to the basically the distance between two layers. You if you want to calculate what exactly my layers is, then you can put a ruler over here and you can measure the distance. If that distance is less than the what the error is mentioning, then obviously these layers have to be moved apart so that TRC error is cleared. And how to move those layers, I think I mentioned yesterday. So there are keys like the numeric keys on your keyboard, 2, 4, 6, 8. Select the layer and try to move it apart from the area where the DRC error is pointing to. Okay, okay. So let me quickly show you this thing live, how to check these DRC errors before we move to LVS. So this was the layout which we were doing yesterday. Let me minimize it. And this console, this is the console window below. So right now there are no DRC errors here. So let me like try to introduce some error here and then we will see. Let me move this. Let me try to add some layer here, metal one. Okay, so you can see I have just intentionally added this layer here, so just to show you how to look at the DRC errors. And this DRC error has popped up here, and this is how it is highlighted here. So now if I want to understand what is this DRC error, just type a command here, DRC find, and it will highlight like what which in which location of, because there might be multiple DRC errors. So this will highlight like this is the DRC error right now it is pointing to, and this is the error. The metal one spacing is less than 0.14 micrometer. So it means like this distance between these two metal one layers is less than zero point 0.1. And in order to see that distance, what I can do, just to build a box over this region. And then if I want to put a scale or a ruler here to calculate what exactly is this distance, there is a command called measure. So this will give you a horizontal distance, but I want a vertical distance. So let me remove this. In order to remove this ruler, unmeasure, and I will put a measure vertical. So it is showing now me the vertical distance. So we can see this is 0.06 micrometer, and this is less than what the DRC rule decks in my PDK are referring to. They say like this distance should not be less than 0.14 micrometer. So obviously this is an issue. Now how I can rectify it? I do not want to move my lower pin layer, but I can move this layer. So let me select it, keep the cursor and mouse and press S key on the keyboard. So this layer will get selected. And now I want to move this layer to the north direction or the top direction. So I will press the key number 8 on my keyboard, numpad key, and this will keep on moving to the top and move it till the time you this highlight disappears or this count goes to 0 or reduces. Okay, so now you can see this has become 0. And just to cross check, although we know like this error, this distance is now more than 0.14, just build a box. Okay, so there's some issue with grid here, but okay, so this is 0.15 micrometer. So I think this is almost 0.14 micrometer here. So this way we can look at the DRC errors in our design and how to rectify it. I think, yeah, I want to remove this. Okay, so this was all I think about DRC error, how to check them, how to measure what the distances are, because mostly DRC errors are due to maybe the overlapping of the layers, or maybe the two layers are very near to each other while drawing a layout. So these are the basic aspects how we can check those errors and also rectify them. Okay, so next step is we will look into LVS. LVS, as I mentioned, I think in my first session also, it is layout versus schematic. So whatever schematic is done, that is electrical circuit which you have validated in your simulations by building test bench and running different kind of analysis, AC, DC, transient, and that has been validated. Like electrical, it is good. While doing layout, you are converting that schematic into a layout that will be physically implemented during fabrication. But layouts are complex. We as of now we are dealing with a very small layout. Like it consists only of two devices and very few, 3 or 4 nets. So it's okay. We know like manually whatever we are doing, it is okay, right? But assume like there are multiple devices there. There are a lot of transistors and resistors, capacitor, everything is there. Let us say 15 or 20 devices are there, and the interconnect between them may go to counts of maybe 30, 40, 50. And when you are doing this manually, there is a very high probability, like maybe you might have done a wrong connection, connected a specific node which has to be connected to node A to a node B, unintentionally of course, or you might have missed some connection in your layout. So these kind of errors are has high probability, and we cannot send over layout for fabrication with these kind of electrical mistakes. So that's the step where we validate like whatever layout is done, whether it is electrically same as our schematic, and that is done through a layout versus schematic check. And how it is done, we know like for a schematic we already had a netlist, and that netlist we imported into Magic, and it was basis for us to start our layout. Now, and after doing a layout, what we can do, we can extract a netlist from layout also, because the layout tool understands like what all layers are there and how those layers combine together to form a particular device. Okay, and how if there are nodes from one device connected to another device node, so those nets are also captured in your layout tool. So the best way to do this LVS check is to extract a netlist from the layout and then compare that netlist to your schematic netlist. And if those two netlists are same, it means whatever things are done in layout, they are equivalent to whatever things you have planned during your front end schematic and simulation design stage. So what is the we already have a layout, and what is the process to extract the netlist? These are the commands. Again, we have to run these in console window. These are 4 commands. I will show you how to run them. Extract do local extract all to spice LVS and extract. So yeah, so these are the 4 commands. Once you run, what it will do, it will extract the layers and their properties, and it will convert these devices and layers in your layout into a spice netlist. And this is the netlist which we will be using for comparing with our schematic netlist. And where this netlist is created, it is again created in your the same directory or same place where this layout exists. So in our case, our layout was in Magic folder, and it again gets extracted by the same name as your layout. So our layout name was cs_am. So this is the spice netlist which has been generated after running those steps. So this is how the LVS netlist will look like. So once these commands are run, as I showed, these 4 commands, this kind of this spice file dot spice file will get generated, and it will these components, and these are the devices or the fingers or the values which have been captured actually from layout now. So now what we have 2 netlists. This one is from layout, and the one which we had extracted yesterday from schematic. So let us have a look at that also. This was the in simulation folder, this one. So this is the netlist which was extracted from schematic. So now we have 2 netlists, and our task during LVS is to compare them and check them. And how to do that? Because for that LVS we will be using another tool called NetGen, which we saw yesterday. Let me show you in the slides. So this is these are the netlist files generated from layout. And in order to run the NetGen, I think you might be remembering on the first day itself, we had created 3 different folders. One was for schematic, another for simulation, second one was for Magic layout, and third one was for LVS, because as we thought like it's good habit to keep the databases separately. So LVS will be run inside this folder, NetGen folder. And this is one step which needs to be done. A link or soft link has to be created to basically bring the LVS tooltext inside this NetGen folder, so that NetGen tool is integrated with Sky 130 PDK LVS rules. So this is the command which has to be run. So let me show you. And then in order to run the LVS, this is the final command which will run LVS check between the netlist from layout and from schematic. So let us quickly see how to do these steps. So from Magic folder, I will go back to my NetGen folder, and in this I will create that link. Uh, okay. So this file already existed for me. It will show you like this setup.tcl. It means this integration between NetGen and Sky 130 PDK is done. Now is the main step how to run LVS. So this is the syntax for NetGen command, NetGen minus patch LVS, and in inverted commas. And the first netlist which I will include is from layout. So my layout netlist lies in inside Magic folder. So I will go inside Magic folder, and the netlist name Spice. And also I need to point out the top name of the circuit there. So that names comes from the subcircuit name of my layout. In our case, it was, I think, CS underscore am. So let us quickly see. Yeah, so this is my subcircuit name, CS underscore am. So that I have to mention here. This is my first netlist. Just to remember, we are talking about LVS, layout versus schematic. The first netlist which I will add in NetGen is from my layout part. So this is the first netlist from layout. Now I have to compare it with my schematic netlist. So that netlist lies in side a scheme folder. In that simulation, and again, its subcircuit name is CS underscore am. Okay. So this is the command, the full command to do a LVS check. And once the command is run, this kind of output you will get, but it's better because output file is also generated once this step is done. And it is called, the output file name is comp.out. So it is better if we see this file inside a text editor. In our case, we have a JVM here. So go inside a NetGen folder and open this comp.out file. And it's better to study here, or maybe what all comparison has been done between these two netlists. So on the left hand side from layout, and on the right side from schematic, it will show you like what all comparison it has done. It has done comparison at the pin level, and then at the device level, and then net level. And at the end you will see this is the like thing of interest for us. If it shows final result circuits match uniquely, it means our LVS check is clear. So this was a small layout. So we know like there should not be any issue. I think most of the connection we have taken care of. So it has matched. There are two devices in my layout netlist, and there are two devices in schematic. Yeah, and there are four nets and same in my schematic. So all that comparison it has done, and finally it has concluded like these two netlists are same or electrically similar. So that's why LVS is clear. So now let us see. I think the thing of interest is what if something goes wrong in my layout. So I will like intentionally introduce some error. I will remove some net. Let me remove this input net. I will delete it. Okay, I will save it. Okay, let me do with output net. So I've intentionally cut this net. I will save this layout, and then quickly I will extract the netlist because now the layout has changed. So obviously netlist has to be extracted. Okay, so now the netlist has been extracted. Let us see if it has updated. Yeah, so this was my layout netlist, and it has been updated after the extraction. And now let us quickly see what happens to my netgen. So the my command remains same because all the netlist files and subcircuit name remains. So I will quickly run this again, and then let me see what happens to my comp.out file, which earlier was showing me successfully. Okay, so now we can see the top cell failed pin matching. So now it is showing like there is some mismatch between these two netlists. So once this is shown, we have to go back from the top or just try to identify what is the issue. So now it is showing like these output pins are not matching because I have introduced some error, and input is also not matching because there is some connectivity the tool makes itself. Like it, if one connection is lost, it might show error due to with respect to that connection in another also. But in this case, we know like this was because the net was disconnected. That's why this error is coming. If we again correct it and through the re-extraction, this result will get restored. So basically, this is an idea to give you like what how we do LVS check, extract the netlist and then compare it using netcheck. It's like quite simple here. But issue generally comes when your layouts are very big, they are very quite complex. Then it takes a lot of time and effort to debug those errors because you have to go one by one, check different devices and nets. If something somewhere wrong has happened, or you have made a wrong connection or forgot to make some connection, that's where the complexity starts. So the kind of circuits I think we are expecting in this boot camp, I think we do not expect too big or very complex designs here. So this step should be an easy one, but still it has not to be taken lightly. Yeah, fine. So this was about LVS. So I think for the small designs, since the areas and the sizes are small, we do not expect like the connections or the nets which are made, the parasitics will be very big for them. So even if you are able to complete your steps till this stage, I think that's okay. I think parasitics won't affect the performance of your circuit too much. But then again, if we go through the complete verification cycle of any typical analog circuit, I think parasitic extraction also becomes very critical. Uh, because as I said, if designs are big, you expect a lot of connections are there. There might be overlap, or two nets are very close to each other, so they might be doing interference. The signals might be interfered because of each other. So all those effects are being captured in parasitic extraction. So let us now go to this step and see how it is done with our open source flow. Okay, so this was about LVS. Yeah. So for parasitic extraction, again, the parasitic has to extract it from the layout. So for that, what has been done is like there's a script written in Tickle inside the console window for parasitic extraction purpose. Just need to source this script, and this script will automatically run extraction. We need not run all those commands because sometimes it become difficult to remember those to remember those and then basically implement and execute those commands one by one. So it's better to compose them as a script and just source that script, and it will automatically do a RC extraction of your layout. So this is what we will see. Once this is done, this kind of big netlist will get generated. Why this is big? Because now apart from your standard components which were used, like in our case we had used an NMOS and a poly resistor. Apart from them, there will be several parasitic elements also captured, and they will be R and C because the nets which have been added manually using metals, local interconnect, metal 1, metal 2, they will have their resistance values. Those number of resistors will be captured in this netlist and also capacitance. So this you will see a very big netlist. But I think the thing of our interest is like we just need to include this netlist and use in our test bench schematic which we had created earlier for front end design, and validate how to whether these parasitics are having any effect or any performance degradation on my circuit. Yeah, so this is how we will basically now integrate this extracted netlist into our front end test bench and then try to run this simulation. So yeah, let us see these steps now. Again, first I go to my layout, And then okay, so this script, I think the script has been captured in those slides also, and I will share the text file also on Slack. But you need to copy that script command, make into a file, and save it inside a same folder where this layout lies. Okay, so let me show you. I'd already done that step. Yeah, so this is that script. Just make open a file and save this command, or if I share it on Slack, just save it in your this directory, magic directory, this script file. Okay, before that, let me also correct this, because if this is not done, our results will be not valid. So source, right? And these commands will execute it in background. And what it will do, it will again generate a netlist along with some other files also inside the magic folder. And this netlist will again be generated by same name, cs underscore am dot spy. So it will overwrite your earlier LVS netlist. So in case if you want to preserve your previous LVS netlist, just before running this extraction, rename that file. Okay. So let us see this file. Yeah. So this is how a parasitic netlist file will look like. Let me show you. Yeah. So these are our fingers, 5 fingers of our NMOS, and this is our poly resistor. But besides it, we see these number of resistors and also capacitors which have been extracted from our layout. So this is something additional, and this was not part of our earlier schematic, ideal schematic, which we use for validation of our circuit. So now obviously once these things are added, there will be some deviation in our results, and this is what we want to see, like after doing layout, whether there has been some degradation in performance due to these parasitics added. If the degradation is significant, and if it is very much affecting my results, then I have to modify my layout to take care, like what maybe if I have used a very long metal wire or some wires, or some nets are very near to each other. So those kind of inferences have to be made and then valid rectified in the layout. But before that, let us see how to run a simulation out of it. But before that, one step which we need to do is just rename the subcircuit of this netlist. Add a PEX besides it. We will see why we are doing this. Okay. And now this netlist has been done, and I will also rename this netlist so that I can understand this is my PEX netlist, not a LVS netlist. Yeah. So once this is done, now my PEX netlist is ready for including in my schematic and test benches for simulation. So I've already built one example. Let me show you what I've done. So, so this was my original test bench, transient test bench, and this was my schematic which I had earlier created for simulation. Let me show you. This was my schematic, and this was my symbol, and these are the test benches. So for running a PEX post layout simulation, and I also want to compare it with my front end, like whatever schematic design I had done. So what I have done, I will copy this test bench as it is, because my power supply and input everything remains same, because I want to do a apple to apple comparison between these two, front end design and my post layout netlist. So this I have done, and but only thing which has changed is the name of this output net, because now this the result for my top upper test bench schematic will be uh, basically run on post layout netlist, PEX netlist. So I want to separate these nodes, and I want to compare what my output results are when I run a same simulation under same circumstances on these two separate test benches, one with front end ideal netlist and another one with post layout netlist. And in order to make this symbol compatible and also include the PEX netlist, I have to do some changes in its properties. So let me show you what uh, has been done. Okay, before that, let me show you what are the properties of this ideal symbol. So the ideal symbol looks like this. Name is equal to x1. Okay. When I have copied this, and then these changes have been made in the properties of this symbol, which includes PEX netlist. So its name has been given same as the name of the subcircuit of my PEX netlist. That's why I had changed its name to. I included a PEX in the name of that PEX netlist here. So this name has been included in this symbol. Okay, and by this second variable, I've included the path of that netlist. So when the xkim will convert this whole test bench into netlist, so the netlist for the upper, this upper symbol will come from this path, and this ideal netlist for the lower symbol will be generated from schematic. So this is the intention of doing this kind of a setup, so that we can do a comparison of both these results in a same test bench. Okay, so once this is done, now let me run this simulation netlist. And okay, let me also show you how this netlist looks like now. Yeah, so now there are two subcircuits. One is this one. This is my ideal from my ideal schematic, and it consists only of this NMOS and this polyresistor. And the second netlist comes from this one, dot include. This is my PEX netlist, which I just extracted from the magic. And this has been instantiated using this statement x2, and this is the name of that subcircuit. So now these two separate subcircuits, one with ideal netlist, another with PEX netlist, will run in the same test bench, and we can compare their results in form of waveforms and operating point values on a same test bench schematic. So let me run the simulation netlist and simulate. Okay, so simulation is run. So first I will see what are my DC operating points. For that I will do control and left mouse button on this launcher arrow. So I can see, I think the input VDD and ground voltages will remain same because they are same for both the circuits. But the voltage of interest is this output. For my ideal schematic, this was 0.87, and for my okay, so there seems to be some issue here. Okay, I think there is some issue with the extraction of netlist. I think it will take a lot of time to debug it now. But earlier when I tried to run this test, it was running fine. So what I will do, I will try to rectify this error and share with you the steps which I have followed. And we can see like if everything is right, that the netlist behind this uh, whatever PEX netlist has been extracted from Magic, then we will see a voltage which will be different from this, because now the effect of parasitics will come into picture. Right now it is not showing right. Maybe something wrong has happened with netlist. So I will need some time to debug it. And similarly, if I load the waveforms, I will see like now I'm seeing only the input and output from ideal netlist, and the output is showing 1.8. But ideally, it should be something similar to this. It won't be exactly same because the effect of parasitics will be there, but it will show like the output, the results of output netlist at the output node will be different from my ideal netlist. So this is basically what is expected. So right now this is not working. Let me look into it, and maybe I will make a short video and also like to find out what is the reason and share with you on Slack. Yeah. So yeah, I think this is all about what all are the steps which need to be followed. I think once this is done, post layout simulation is done, and you are happy with the results. Let us say if all the waveforms are matching and whatever, if we are interested in some kind of AC analysis or transient like slew rate or some kind of a rise time, fall time, and all those specs are meeting after, even after the parasitic extracts are taken care of, taken into consideration for simulation, then I think the design is okay, and we can go ahead with sending it for fabrication. So these steps are required. So okay, one more point I want to emphasize is like for a foundry or a fab, whichever it is, they are not like interested in whether you have done your LVS or parasitic extraction, whether your specs are meeting or not. The only thing which Foundry cares about and they are interested is in like your layout or GDS which you are submitting to the fab or Foundry should be DRC clean. Okay, so these checks, LVS, PEX, post layouts, validation of your layout, these are for the designer's own confidence. Like you want to be assured, like whatever designs you have done, they are okay, electrically fine, and whatever you fabricate, and once the chip comes back to you, you expect to see those results on your during your measurement. But from a Foundry's point of view, they are only interested like whatever limitations or specifications regarding the manufacturing which are captured inside the DRC, they should be obeyed and respected by the design which designer is sending to them for fabrication. I think their consideration is only that much. In that design, whether LVS is done, PEX is done, I think that's none of their business. They are not uh, worried about that. Yeah, so it's important like DRC should be clean whenever you are sending your fab layout for tape out of a fabrication to any foundry. Yeah, I think that's all for today. This specs thing, which I think which I was not able to successfully demo, I will try to rectify and share with the results on Slack later on. So anybody has any queries till now for DRC, LVS, and PEX?
Sir, what changes we can expect after the post layout simulation? Like, if we have not done the proper matching or common centroid layout, so exactly
Uh,
what things do we need to keep in concern when doing the layout?
with respect to common centroid layout is important in certain aspects where the matching of your devices is very critical. So in case of let me give an example. If you are doing an op-amp, so in op-amp the matching of your input transistors becomes very critical, because if there is a mismatch in them, it will lead to offsets. Okay, so it's not like matching is required for all other components. For the like for a tail current source or some output second stage of an op amp or some others, it's not matching is not important. Matching is only important for certain particular components which requires that kind of limitations, because if these are not met, there will be issues during after layout, because there will be difference due to the processing of your circuit or devices on a wafer. So these things will reflect there. Again, coming back to this point, if you are talking about an op amp and if there is a mismatch between your input and you will see offset effects in your layout on your chip during measurements. Yeah.
So, sir, I will need to keep in mind about differential pairs, current mirrors, and those kinds of things.
Yeah, those needs to be taken care of. But it's not like your circuit won't work. Okay, it's the only thing if let me try to explain you. If you are doing a very high end product, like if you it's very critical and you want to ensure like this thing is a first time success, passes everything. So that in that case, you definitely need that kind of a validation. Like you need to ensure like I follow all those steps. But specifically talking about this kind of a scenario where like we have a limitation, we are not building it for a product, we are building it for our own learning and our own satisfaction. Like I want to get an experience of basically taping out a design and able to measure it. So if you try to follow each and every step to the point, like a lot of time you will consume for doing a common centroid layout to ensure the matching, etc. So in that case, you might miss the window of submitting your design. I'm talking about this particular scenario. Or even in companies, if, for example, they are prototyping, they know like this design, we want to prototype it in a very quick time. So they want basically they just want to ensure like whatever concepts we are thinking about, is it working or not on silicon. So in that prototyping phase, they won't try to do their best design. Their main target is to like follow the time schedule of a shuttle and try to make design ready so that it can be put on that shuttle. As you can see, there are a lot of steps involved. Okay, so if you are really worried about ensuring like these specs are very sacrosanct for you, like you do not want to compromise on them, then definitely go for common centroid layout and all those aspects which are necessary, that has to be taken care of. But if you have a limited time period, so I suggest like do not go strictly by that those consideration, because your main target should be like your design should be ready in this stipulated time period and ready for sending for fabrication. Because if this uh, the kind of a duration is missed, I think the next, I don't know when you will get a next opportunity to send your design for fabrication. So that's my piece of advice in this case.
Sir, exactly how long time do we have till tape out, till the final GDS submission?
So yeah, that's what I mentioned. By 30th April, by end of this month, you should be ready with your design. When I say ready with your design, you should have a DRC and LVS clean GDS shared with me. Okay.
Okay, sir, that's too less of a time, I think, than for
No,
this
it is
post
possible.
PEX.
If you, that's what I'm telling. It might look difficult. Obviously, it is difficult. It's not easy, but it is possible. If you try to pick a small circuit, don't go for a very fancy design or something. That's what my advice is. Try to learn these steps as quickly as possible and try to implement it. Because I have seen in past students being able to do this kind of activity. That's what I'm telling.
Okay, sir, then I will go for a very basic design like CS amplifier only or some very single
Uh,
stage amplifier, that kind of
CS
thing.
amplifier is a very like a very preliminary circuit. I suggest like if you can go for a differential amplifier, let us say, okay, or maybe if you can add a second stage also, because it requires 6 to 7 transistors, or maybe some kind of a ring oscillator, inverter based ring oscillator, or maybe a very basic band gap reference. So I think these, if you want to do a CS amplifier, that's okay, but because at the end of this event we will be selecting the design which is the best out of all, because we can accommodate only one design. Okay.
Okay, sir, I have till now designed two-stage Miller amplifier and rail-to-rail swing amplifiers. So those are two
Yeah,
of the complex designs.
yeah, that's good. I think if you can do a Miller op amp, I think that will be very good for this kind of activity.
Okay, sir, I will try my best.
Sure, sure. I think there is one question on chat. DRC error free layout is the final GDS file. Yes, so the final GDS which fab will accept will be, there should be no DRC error. Okay, let us say if you send GDS to a fab which is LVS clean and your specifications are meeting, everything is okay, but it has even 1 or 2 DRC errors which are not acceptable to fab. So they will reject your GDS. So that's what I'm telling. From fab point of view, because these DRC rules are basically related to their manufacturing processes. So they do not want to compromise their manufacturing processes due to DRC, because this will directly affect their yields and other aspects which takes place inside a fab. So it's, they are very particular about it. Like you should clear all your DRC errors, and only zero DRC error GDS should be submitted to them. They are not worried about whether it is LVS clean or PEX cleared, but they are very particular about DRC errors. It's important. Any other questions or?
Sir, I also wanted to ask about electrical rule check. Like, what is that? Can you just explain?
So ERC rule checks are a bit complex. I think there are some electrical rules, like if there are latch up effects or some other effects which are basically inbuilt into your PDK. So for certain circuit configurations, these are not mandatory, but these are required for checking the robustness of a circuit. So those kind of effects are, might not affect your circuit's performance. So those are called electrical rule check. So they basically check the electrical properties of your circuit, uh, because ultimately everything is in form of physical processes of fabrication, doping and implant and everything. So ERC rule checks basically validate whatever circuit you have drawn on a layout, it is electrically robust. But it's not a mandatory check. It is optional. If a designer wants to check the robustness of circuit, they can do it. And not all foundries provide those in their PDKs. But some foundries, they provide it as an extra feature in their PDKs.
Okay, sir, got it. Sir, I wanted to ask that Sky 130 is a 130 nanometer node, so we would also like to take in account the second order effects, right? There will be some MOSFET second order effects which would affect our design.
So okay, so we from theoretical point of view, ideally you should take those things. But what happens is when because this is what if you try to do these things on pen and paper and theoretically it takes a lot of time. So that's why these tools and simulators are available with you. Okay, so for example, if you want to check whether what is my channel and modulation or some how is my VTH is affected, so all those analysis you can do in these simulators. Okay, and as you get hold of the PDK, like if you start working on it for a long time, then you get to understand the properties of those devices, what kind of like performance they give, and what are the effects which they might be important for the designer for a specific circuit point of view. So with experience, those things come up. But initially, if you want, you can use a simulator and whatever schematic tools are available. You can build your test benches or your test cases to calculate those second or third order effects if they are really important for your design, and that's how you can get this.
And sir, I wanted to ask whether it's a hard requirement to use open source tools because I'm having access to Cadence tools and Sky 130 PDK from Cadence website.
Yeah,
So,
so it is a hard requirement because this initiative is being like sponsored by IEEE Open Silicon program, and their mandate specifically is like they want to promote open source softwares, especially for academia and research. Because okay, not everybody around the world or even in India has access to Cadence, or even though government is pushing it. And also there's a high chance like in future because I think you must be knowing these are very costly tools. Even for academia you have to pay large sum of money. So the new trend which is coming up and which the IEEE is promoting is like at least for academia, because most of your designs are not going for fabrication. Academic designs are mostly for learning purpose or maybe for research purpose. Those kind of things can be very easily taken care of in with open source tools, and there is no restriction on them. So and that's why, because we have to show to the IEEE like whatever things we have done in this bootcamp are being done with open source tools. So I think it's important you stick to open source tools. If you do it with commercial, I think we won't be able to accept it for fabrication.
okay, sir. So like I can use Magic and K layout and those kinds of tools.
Yeah, so K layout you cannot use with Sky 130 PDK because PDK is not integrated with K layout. But Magic you can do the way I showed you. So for a schematic, you have to use Xscheme and ngSpice for simulation. They are integrated together, and layout with Magic and LVS with NetGen. These are the four tools which will be required.
Okay, sir. I have set up the Docker container. I will try to do the simulations today.
Yeah, sure. Please, if you have any issues, please put it on Slack.
Okay, sir. I guess those are all the questions from my side. Thank you.
Sure. Thank you. Thank you, Faith. So thank you, everyone. I think it's a good opportunity. Again, I would advise. Okay, it might look a little tricky using open source tools, especially if you have already used Cadence. But I think the biggest benefit is like these tools will remain lifelong with you. You need not, if you go out of your college or institute, still they will be there. And if you build like a competency on using these tools, so there are other PDKs also available like GF 180, ISP 130. So there are a lot of things happening in this open source domain, and now even commercially companies are doing work. So maybe from career perspective also you will might be getting a good opportunity if you are knowing about open source tools. And yeah, so that's my advice. Please take benefit of this opportunity and try to build some design and try to learn them. And yeah, and if any queries, please most welcome to put them on Slack. Okay, so we can conclude for today.
Yeah, yeah, sure.
Okay, thank you everyone, bye.
Thank you all. Have a nice week.